So we've talked about what these substitution reactions are. We've talked about why they happen. We've talked about what the transition state looks like. We've talked about the mechanistic details. We know the transition state's high in energy. We know mechanistically there's backside attack that occurs. Question is, how else can we kind of assess what's going on in these chemical reactions? Well, you have a variety of different variables that can actually be manipulated, and that can influence the way that the chemistry actually proceeds, the actual kinetics of the reaction. Now, remember, this really is kind of thought about like a kinetics kind of a thing. You want to think about how the nucleophile is going to bump into the electrophilic position. And if the two of them can't find each other, the chemistry is not going to happen. All right, that's the big takeaway right here. So if an electron-rich nucleophile can't find the relatively electron-poor electrophile, no chemistry is going to happen, right? Mr. Right can't find Miss Right, right? The two of them can't find each other. There's going to be no productive chemistry right there. All right, so we can look at this a variety of different ways, and this is sort of the generic expression for what we're seeing here. So we have our alkyl halide, again, just to apply the color scheme so you guys are familiar with this. Our alkyl halide is composed of an electrophilic position, a leaving group, and then basically an electron-rich nucleophile. This is the pattern that you're seeing in this case, right? So the electron-rich thing, red, attacks the blue thing, and then the leaving group, the orange thing, goes away, right? This is the pattern you see over and over and over again. All right, so let's look at a variety of these different factors that go into these SN2 reactions and see how does that influence the ability for the nucleophile to attack the electrophile. So our first one we're going to look at is the actual structure of the electrophile. So what we're looking at here are two different chemical reactions. We have a fast one that's occurring and a very slow one that's occurring here. And I went and modeled out the LUMO for both of these really quickly so you can kind of see what this sort of looks like here. You'll notice the LUMO looks very, very similar to each one of these here, but there's a big difference in terms of the reaction rate. And the reaction rate here, when we're talking about the electrophile structure, what we're really getting at here is that we want to know, is this a primary? Is it a secondary? Is it tertiary? That's what we're getting at with these types of problems here. All right. So when we deal with the electrophile structure, let's apply our convention to this. Right. So we've got our leaving group was orange. The leaving group is connected to the electrophilic position, and the electrophilic position is touching how many carbons? The blue is only touching one carbon. So this makes this what? What type of an electrophile is this? Primary, secondary, or tertiary? This is primary. Let's look at the slow reaction. All right, so we had our leaving group is touching the electrophilic carbon, which is touching 1, 2, 3 carbon atoms right there. So what does that mean? How do we classify this electrophile? It's tertiary. Tert, you're right. That's where we get that tert butyl from, or the tert butyl alcohol or tert butyl bromide. Exactly. All right, so why does that matter in this case? All right, you're an electron-rich species. You're a really, really good nucleophile. You're coming in, and you have a choice between the two of these. Now, they have similar energies with each other. We can compute them and see what their LUMO energies are. Which one of these am I going to want to attack more? The one on the left or the one on the right? And then why? We like the one on the left better. Why do we like the one on the left better? Easier to get around it. You only have one carbon group in the way. So if you're like a nucleophile, all you got to do is kind of, this is your nucleophile that's right here. He's just got to kind of come in and that's it. He's just got to find that, no problem, right? He's got a bunch of different ways he can attack. And really, there's only just a teeny little bit of carbon that's in the way, and that's it. Now, why is this different than what's going on over here? Why is this so difficult to get in here? Well, remember, look at the carbon atoms. These all represent bulky electron density around here. So I like to use the analogy, I know we used this last class, I like to use the analogy of a pilot in a plane trying to land on a runway. Would you rather land on a runway that's a primary alkyl halide, that is, there's no trees around it, Or do you want to land on one where the runway has a whole bunch of trees running up against the runway right there? It's a tertiary one. Which one's easier to get into? Okay, maybe that's not the best answer, right? Maybe we want to think about it from Publix parking lot perspective here. Which one's easier to find a parking space in? 7 o'clock in the morning when there's nobody at the store and the store just opened, or 4:30 in the afternoon on a Sunday when it's all undergraduates zipping in and out? Which one's easier to find a parking spot? The first one, right? So the first one is like, think about a primary alkyl halide is like an empty parking lot. Think about a tertiary one as a full parking lot. Now, the effect that we're referring to here is called steric bulk. So as we start to increase in the amount of electron density around that electrophilic position, you are increasing the electron clouds around it. You are increasing in steric bulk. There's a size effect, right? You have those methyl groups are crowding that electrophilic position. Down here, you have very minimal steric bulk. So in instances, especially for SN2 reactions, in instances where you have lots of steric bulk, the reaction tends to slow down. Whereas if you have instances where you have very little steric bulk, the reaction is actually quite quick. Okay, electronic or electrophile structure. That's one aspect of it. Bottom line is you want your electrophiles to be small. That's kind of what we're getting at. All right. Number two, the leaving group. So let's talk about the leaving group. What am I talking about in a leaving group here? So let's classify what's going on here. So in our first example, the fast reaction, our leaving group is a bromine. In the second example, what's our leaving group? The really slow example, what's our leaving group? What's the thing that went away? OME, right? That's the thing that goes away. This is our leaving group right here, right? That's the thing that fell off there. That's the thing that fell off right there. All right, so let's look at these really quickly here. So our leaving group here was Br minus. And then the leaving group here was OMe. OMe, methoxide. All right, now there's a slight typo here. It says leaving group conjugate base, CB. This is actually the leaving group conjugate acid is what you want to look for. So let's look at the conjugate acid. How do I take a base and turn it into a conjugate acid? I just add H plus to it. That's all I've got to do. So we're going to take this thing and we're going to just add H plus to it, and it becomes HBr. Okay, same deal with methoxide. If I want to take this base and I want to turn this into, let's see if I can redraw that. Hold on. Plus H plus. This is going to turn into HOME. So methoxide or methanol. All right, so now the question becomes, what is the pKa value for each one of these? So HBr, pKa value for this is what? Positive or negative? Negative means wicked strong, strong acid. Positive value means not strong. It's a weak acid. It is a strong acid. And why is that so important here? It has a pKa value less than 0. I think the value, we looked it up the other day. I think it was what, -9 or something like this? Okay, so you say, why do we care about the pKa value in this case? Well, if it's -0, it's less, -0, it's less than 0. It's a strong acid by definition. That's the first part of it. But more to the point, strong acids have conjugate bases that are what? If they're strong acids, that means they're good acids, which means the conjugate base is bad. It's a weak base. It makes a bad conjugate base. So this is the point right here. This is the logic. And this is a tough thing for a lot of students to wrap their head around here, is that whenever you have a bad conjugate base, whenever you have a bad base, something that's not basic, something that doesn't want to react with anything, it's generally stable. That's the important point here. So this is actually telling us here that since this is a bad conjugate base, this actually is very stable. So what do we want in a leaving group? We want stable non-bases, things that aren't very basic. How is that different than what we're seeing in the case of methoxide as the leaving group? All right, well, let's take a look at it. So we said that methoxide was the leaving group. The conjugate acid of methoxide is methanol. What's the pK for methanol? You may not remember this off the top of your head. Hopefully you do. 15 to 19. Bottom line is that it's positive. Greater than 0. So what does that tell us about the acidity of this? Said if it was negative, it was a strong acid. It was a good acid. If it's positive, what is that telling us? Weak acid, exactly. And so if this is the weak acid, what does that tell us about the conjugate base? Strong conjugate base. Strong, by the way, is synonymous with good. So since it's a strong base, here's the deal. This strong base means that the base must be reactive. You don't want your leaving groups to be reactive. You want them to go away. And to go away means that they can be stable when they fall off of that carbon. So what are we looking for in these cases? Strong acids, well, we want weak bases, right? We want things that are weak, that are poor bases to fall off is the key here. And then methoxide, of course, is a very good base. So we should be able to kind of get that all figured out right there here. So that's how we think about leaving groups, right? So we want things that are easy to fall off, that are non-reactive, that are nice and stable. We want our electrophiles to be small and compact. What's the other factor? The nucleophile. All right, so we have two reactions to look at here. Our first reaction we have is fast. So we have hydroxide is reacting, talk about our nucleophile here. It's electron rich right there. And it is reacting with what? The electrophilic position, and then the chloride is the leaving group right there, right? So something's going to come in. And by the way, this is very, very fast. But if I replace methoxide with isopropoxide, so this is isopropyl alcohol, you've removed a hydrogen from it. Isopropoxide, good word. Blue. This is orange. The reaction's slow. So what's the difference between hydroxide and isopropyl or isopropoxide? What's the difference between them? Let's think about the structures of them. Look at the structures of them really quickly. Let's see, hydroxide, OH, is just comprised of two atoms, an oxygen and a hydrogen. So what's its size look like? Is it big or small? Two atoms, big or small? Two atoms, big or small? Think about it. If you're something and you're only made up of two atoms, teeny, 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 teeny. But look at how many atoms are present for isopropoxide. You have an oxygen, 3 carbons, and a whole truckload of hydrogens on there. So by comparison, which is the bigger of the two? The one on the right is bigger. So what is that telling us right here? As I start to make my nucleophile bigger and bigger and bigger, what happens to the reaction rate? Slows down, exactly. So what this is basically telling you here is that if you want a nucleophile to react in an SN2 reaction, you want small nucleophiles. That's one aspect in this, right? So the one on the right, slow reaction, is too big, right? So it has lots of steric bulk. So sterics are going to slow the rate of the reaction down. That's one side of it. Okay, here's the other side of it as well too. Reaction 2. So we do this with ethoxide, which is pretty small, I would say. It's very linear looking. It's very arrow-like. Kind of think about it this way. And the oxygen is going to attack that carbon right there, that electrophilic carbon. Chlorine's going to fall off in this case to make, this is diethyl ether. But then if we repeat this experiment with acetate, that's what this is, what you notice here is that the reaction goes a little slower. Okay, so why? What's actually happening here? What's the difference between ethanol and acetate? I'll give you a huge hint. You ready? That carbonyl right there, that's a big problem. And you say, well, why is that such a big problem? Well, anytime you have a pi bond that's next to an oxygen or next to an atom that has a negative charge on it, kind of think about this here for a second. We can draw multiple resonance structures for this, right? So we can actually draw out a resonance structure that looks like this. These are the same molecule. We've just moved the placement of those negative charges around a little bit. But more to the point, you have a resonance hybrid that looks like this. That's the hybrid right there. Why is the hybrid so important in this case? Resonance is a stabilizing effect. If you can take that negative charge and you can spread it out over multiple atoms, you're effectively stabilizing that molecule. Now, why is that so important? If I stabilize the molecule, what's happening to the reactivity? If I stabilize the molecule through resonance, what's happening to the reactivity? Decreases, exactly. So this is the point. Resonance stabilizes the nucleophile. And since it stabilizes the nucleophile, it is going to decrease the reactivity of the nucleophile. Now, do we see the same effect in oxygen in the ethoxide? No, we do not. Okay, so what's going on here is you have, if you kind of think about it here, and go back to the acetate here for a second. So in the hybrid, which represents the molecule in reality, it kind of looks something like this. You have electron density that's shared over multiple atoms, right? So you have kind of like two electron-rich species instead of focusing it on one single atom. Here, you have all the electron density is focused just on that single oxygen atom. This is what we call localized electron density. Anytime you take a charge and you stick it on one atom and it can't move around, it can't be stabilized through resonance or electronegativity or anything like that, you tend to increase the reactivity of it. So you see a decrease in stability and more. Oh, I misspelled that. Guess we can stibil. And then we increase in the reactivity. Point being, this is increasing in its nucleophilicity. All right, so here's the point. Resonance in the nucleophile slows the reaction rate because you're able to take that electron density and spread it out over multiple atoms. Okay, so there's a lot of factors to consider. Not only do you want small nucleophiles and small electrophiles, but your nucleophile has to be stuck on a single atom. It has to have small localized electron density. If you meet that bar, you become a fantastic nucleophile. I like to think about when I was a kid, I had a friend growing up who had he had every Nerf toy known to man. And one of the toys that he had was the Nerf bow and arrow. You know, the Nerf bow and arrow, the one you pull back and you can actually shoot darts at each other, not knock each other's eyes out. I always think about that when I think about SN2 reactions. You know, drawing back on that thing and you're shooting an arrow. Nucleophiles are a lot like arrows. You want them small, localized in the point in one particular location right there. And that's what's happening here. You'll notice this hydroxide here, very arrow-like. It's small, it's compacted. Electron density is focused just on the oxygen atom. Same deal with the ethoxide as well too. Small, compacted. Electron density is stacked just on the oxygen atom, and that's it right there. So these are fantastic, fantastic nucleophiles, and that's another factor to consider when you're looking at the rates of an SN2 reaction.